All right. Thanks. Okay. Yeah. So this is very important. Okay. So this for a partition P tilde of for a partition P and its refinement P tilde, you have this lower sum is less or equal to the lower sum of the refinement. Similarly, the upper sum of the partition is greater or equal to upper sum of the refinement. All right. Now, this we have proved. Here, the problem was, see, I had taken P and its refinements, right? Its refinements. And what we get is this this kind of inequality. The question was, well, the supremum over. So, question was this over this partition whether this exists and whether this one exists. Of course, we need to take common refinement, but there will be a better way to explain, and that is what I'm going to explain now. Is about this correction. So suppose P1 and P2 are two partitions of AB. All right, and that would actually give me, and let P tilde be a common refinement of P1 and P2. So what we have is the lower sum of P1 for the partition P1 is less or equal to lower sum of A for the partition P tilde, because P tilde is a refinement, right? And then this one is less or equal to, let me shift this a little bit. Yeah. This is less or equal to upper sum of A for the partition P tilde. Right, so this we have proved the last theorem, and since P tilde was the refinement for P2, so this should be less or equal to P2 comma L. All right. Now you see here what we have is actually what we get is this L1, sorry, L P1 F is less or equal to U P2 of F. Now here you can take supremum, supremum, and here you take infimum. So you take supremum over partition P1 P1F, right, less or equal to U P2F. So this one will be A to B lower integral f dx, and so this will be, again, one can take infimum over P2 U P2F, which will be integration A to B upper integration fx dx. So fx dx. All right. Yeah. So the next one is what we stated last time as well, that this is very important theorem. This will be used to prove certain, I mean, for a class of functions, so that this is integrable or not. To see this one, this theorem will play a vital role. You will see. for even continuous functions, we'll see by using this one that any continuous function on a closed interval is Riemann integrable. All right. So I have written this one already. A function f on AB is Riemann integrable if and only for every epsilon greater than 0 there exists a partition P of AB such that UPF, the upper sum minus the lower sum of that partition, is less than epsilon. All right. So the idea to prove is to use this stuff, that upper integral is less or equal to lower integral is less or equal to upper integral, and any lower sum is less or equal to the lower integral, and any upper sum is greater or equal to, right, greater or equal to the upper integral. So here we use that. So first to assume this one holds for a partition. So what does hold? Given epsilon greater than 0, there exists a partition P such that star holds, right? So this holds. Now by previous remark, lower sum for the partition P is less or equal to the lower integral f, right, less or equal to the upper integral, which is less or equal to the upper sum. So let me shift towards the left. PF. All right. Now call this 1. Now what we have is UPF minus LPF is less than epsilon, right? We have by star that UPF minus LPF is less than epsilon. This implies the upper integral fx dx minus the lower integral fx dx is less than epsilon, right? Which lies in between this. An upper integral is bigger than lower integral, is greater or equal to 0. Since epsilon was chosen arbitrarily, maybe let me shift this a bit, because I need little more space. Chosen arbitrarily. what can you do since epsilon was chosen arbitrarily? This is true for every epsilon, right? This, let me call it 2. So 2 holds for every epsilon greater than 0. Hence, it has to be, you can take epsilon tends to 0. So that implies the upper integral fx dx has to be equal to the lower integral fx dx. Therefore, f is Riemann integrable. All right. Now we look at the converse. Any question here? Right. So this is simple. The both side you have that this difference is less than epsilon. The difference between in the middle will also be less than epsilon, and since epsilon was arbitrary, we have the proof. Now here assume f is Riemann integrable. So we have here these two are equal, right? Then we need to show that for every, so assume f is Riemann integrable on AB, and what we need to show that for every epsilon greater than 0, there exists a partition P of the interval AB, closed interval AB, such that UPF, the upper sum minus the lower sum, is less than epsilon. So the idea is to unfold the definition of lower and upper integrals. So what actually means is the unfolding the definition of supremum and infimum. All right. So this might look a little boring at this moment, but the important question what we are addressing is to find class of integrable function. Our aim is not to evaluate the integral. Our aim is to find or to try to get a good class of functions where the integral can be found. Okay, so in general, the methods does not give exact integration all the time, but what are the integrable functions where integration exists? That is the question we are dealing with, and that is the reason it is little bit abstract. All right, so we need to prove this one. So how would one start with? Can you give me an idea? Well, ideas, of course, there to unfold the definition of lower and upper integral. So what does it mean that by that?
We use
What,
the monotone convergence sequence to uh, find out the supremum of the lower sums and the infimum of the upper sums. So
Mhm.
uh, that means that there exists at least one partition which
Mhm.
lies in epsilon by 2 neighborhood of uppers of the upper infimum of the upper sum, and a partition such that it lies in epsilon by 2 neighborhood of the supremum of the lower sums. So we can take the common refinement and it should suffice.
Right, right. Exactly. That is the proof. So what do we do? Fix first epsilon. Fix epsilon greater than 0, and since this upper integral a to b fx dx is infimum over all partition P, right? Upper sum of A with respect to that partition, what you get is there exists a partition P1 of AB such that the upper sum with respect to P1 minus the upper integral is less than epsilon by 2. Alright? And similarly, since the lower integral is supremum over all partition of the lower sum of F with respect to P, there exists a partition P2 of AB such that the lower integral minus the lower sum P1F is less than epsilon by 2. Alright? Yeah. Now what would you do? So since we have taken F to be Riemann integrable, since F is Riemann integrable, so I write Ri or just to abbreviate. Upper integral fx dx is actually the integral fx dx, the Riemann integral, and that is equal to the lower integral fx dx. Right? So we just add these two. Right? So add 3 and 4. So what we get is, well, there is one more step before adding. So here, we get P2, right? So here, this is with respect to P2, not with respect to P1. So let P tilde be a common refinement, of P1 and P2, right? Now, once it is true, this 3 and 4, it is true for P1, it will be true for any refinement of it, right? So in case of upper sum, the refinement will be smaller, right? So what we get is u p tilde f minus integration a to b fx dx is less or equal to u p1f minus integration a to b fx dx, which is less than epsilon by 2. This is 5. And integration a to b fx dx minus L p tilde f, the lower sum, is less or equal to integration a to b fx dx minus lower sum with respect to p2 f, which is less than epsilon by 2, 6. Right? Now we add it. Need some more space. So now we add five and 6. So and obtain UPF capital F minus L capital F is less than epsilon. Right? Is this clear? Is this clear?
Yes, sir.
Okay. Yeah, so it was Sadbab, right, who said that the full proof basically, right? Yeah. So I can't see who's speaking that time, who spoke. So was it Sadbab?
No, sir.
Oh, who was it?
Sir, I'm Akash.
Oh, you're Akash. So did you read integration? And did you read
Uh,
the notes?
no, sir. I did it in last semester. Sorry, in first year.
Oh, okay. Yeah, anyway, that is fine. So your actual idea is just making this formal. Whatever you said does the job, right?
Yes, sir.
Yeah. So this is very important to understand that this one, though it looks a little bit abstract, this upper sum minus lower sum, but it actually gives useful stuff. So next theorem will show that for any continuous function, so any continuous function is Riemann integrable. So at least we should have some class of functions, right? Which can be integrable, which will be integrable, right? So here, see, the scheme is we start with continuous function, then we keep on adding discontinuities. Okay. So the general idea is at the continuity, when function is continuous, in a neighborhood of any point, functional value is very small, right? To small to each other. So what I mean is the following picture. Okay, so what was the point was, here it is, the following picture. So if you have some continuity, so suppose you have something like this, some discontinuities. Of course, this is not state functions, but looks like that. Now at the point of continuity, so this point it is continuous. If you make this neighborhood small, if you make this neighborhood small, the functional value remains small, right? So if the partition is this small, then the infima of the function in that partition, in that small interval, and the supremum of the function in that interval remains very close. All right. The only problem when there is some discontinuity, you see here the supremum and infimum differs by quite a bit, right? So there is this problem when the function is discontinuous. But for continuous function, this is what we need to do. That the lower sum, I mean this supremum of f and infimum of f will be very close. So lower sum and upper sum will be very close, and that is what it is. Right? If you take the partition to be very small, which means the partition should not depend on the point, which means the length of the each partition, let's call it delta, should not depend on the point. What does it mean to function for the function now? Do you see? So if you consider the length of the partition to be delta, then in the delta neighborhood, the functional value remains close, right? I mean, in a small epsilon neighborhood. But now, as you vary to other points, we are not considering this discontinuous case. We are considering this case. So as you vary the points, or if you look at a different partition here, then so this the length of the partition here, I said delta, here it might not be delta. That could be a problem. What we need is the same delta should work whatever the partition you choose, right? Which means uniform continuous. And that is the reason you see we have taken closed interval, continuous function on closed interval. So this is an exercise which is actually you have done in the last semester. Any continuous function on closed interval is uniformly continuous. So uniform continuity is important. All right. So now continue of the proof. So this was an exercise. So fix epsilon greater than 0. So what do you want to find? A partition P of AB such that the upper sum of F with respect to P minus lower sum of F with respect to P is less than epsilon. Right? Now, what you want to do is the following. Since F is uniformly continuous on AB, Since f is uniformly continuous in AB, on AB, we have this epsilon, so there exists delta greater than 0 such that mod of x minus y less than delta implies mod of fx minus fy less than epsilon by b minus a. All right. So epsilon by b minus a is to make this one to be epsilon, nothing else. Now, so next is now make a partition. So consider a partition. P, which is x naught a less than x1 less than equal to x1 so on to be of AB such that xj minus 1 is less than delta. All right. All right. The length of, which means the length of the each subinterval is less than delta, which means the length of each subinterval is less than delta. So this is required. All right, this is required for what? Just for this one. It will be closed, right? Supremum will be closed to infimum. Now, the lower sum, sorry, LPF minus, sorry, UPF minus LPF. Let me put it in that way. UPF minus LPF. What is it? It is summation j from 1 to n capital MJ xj minus 1 minus summation j equal to 1 to n small mj xj minus 1. All right, where mj is supremum of f over xj minus 1 to xj, and small mj is infimum of f over xj minus 1 to xj. All right. Now, which is equal to summation j equal to 1 to n capital Mj minus small mj xj minus 1. All right. Now, by, I should give it a name. This is 1 by 1 by 1. Sorry. Since f is continuous on this interval xj minus 1 to xj, the supremum and the infimum are attained. That means there exists the j and sj in this one, xj minus 1 to xj, such that mj is f of tj and small mj is f of sj. Now by 1, mj minus mj, which is equal to mod of f tj minus f of sj. This should be less than epsilon by b minus a, since tj minus sj is less than delta. All right. Now by 2, so from 2 we now get, from 2 we get that the upper sum minus lower sum will be equal to summation epsilon by b minus a, xj minus 1, j from 1 to n, which is epsilon. This is right, which is what? Less than epsilon. Sorry, here it is less than. All right. Therefore, by previous theorem, f is Riemann integral. Yeah, is this fine? The proof? Yeah. So what you use is basically this one, and making partition so small, and then upper sum minus lower sum, there is this term which will be less than epsilon by b minus a. Yeah, so is this fine? Yeah, I'm already 7 minutes delayed. What was that question exactly? Exact question in the assignment?
It was the Taylor series expansion of the last thing.
Yeah, so I mean, what was the question? What was in? Oh, so it was, I think, minus. So it is e to the power 1 over x square, right?
Yeah, so it will be minus, right? Because our tutors are also a bit unsure.
Yeah, it would be minus.
Okay, thank you.
Yeah. Okay, so any question here? Yeah, so let the others know that it will be minus. Let me stop sharing.
Sure.
Yeah. Yeah, okay then. See you later.